The title of the presentation is Adaptation Works to Avoid the Flooding of Piazza San Marco in Venice, Physical Model Tests to Evaluate the Overtopping Discharge. My co-workers are Chiara Favaretto, Matteo Volpato and Piero Ruol. My name is Luca Martinelli and I am Associate Professor at University of Padova. You're certainly aware of the Mo.Se system of gates in Venice, placed at Porto di Lido, Malamocco and Chioggia, which is designed in order to keep the water level in the lagoon below a certain level. This level is 110. That was chosen as a compromise to achieve safety within a limited number of closures per year, thus allowing for a sufficient water circulation in the lagoon. However, even the Mo.Se cannot avoid the flooding of Piazza San Marco, since the floor of the piazza has a very low level and additional works. The lowest parts of the piazza have an elevation of approximately 87 centimeters, and during high tide, for instance, consider that last November tide was 187 centimeters, the piazza is obviously flooded. Flooding occurs through the drainage system, as you can see from the video. The water flows through the sewer drains or manholes. When the Mo.Se will be operational, it will preserve a level of maximum 110 centimeters. It will then become possible to avoid the flooding thanks to other specific works, mitigating the return flow through the drainage system, filtration, overflow through the boundaries, and overtopping, which is a topic of this work, of this presentation. The expected overtopping discharge was studied in a previous paper, and it was found excessive for the new envisaged pumping system. So this presentation focuses on the adaptation measures to reduce overtopping for the piazza. In particular, a small temporary barrier, vertical and 40 centimeters in height, placed along the critical stretches of the quays. This video shows the overtopping mechanism that we are studying. We see that the water elevation due to tide is approximately at the same height of the quay elevation, and therefore just small waves can produce overtopping that flood the piazza. I will first present the investigated area, then the forcing conditions, the sea level and the waves that are expected when the Mo.Se will be operational, and in these conditions what is the expected overtopping in the absence of adaptation measures. This is already published material, but in this presentation we will focus on the suggested adaptation measures and on the expected overtopping with the adaptation, and then the conclusions. The Venetian lagoon is located in Italy. This is Italy. This is the Veneto region, very close to the Adriatic Sea. We have this lagoon with the three mouths where the Mo.Se will be installed, and this is the city of Venice, and this is the San Marco Island or San Marco Piazza with the square which is so frequently flooded. This is a particular of Piazza San Marco, just where the quay is present, and the quay is divided in three sectors, A, B, and C. A and B are vertical walls, and C, in the part C part, there are descending steps. The edge of the quay here is approximately 100 centimeters over the chart datum, meaning that it is even below the maximum expected water level even when the Mo.Se will be operational. But as you can see here, there are in color scale, there is the bathymetry, and in dotted lines there is the highest part of this piazza, because the floor is a little sloping downward in the inside and also sloping downward in the outside. The red part here, in this area where the black points are within the red area, the level is approximately 117 centimeters, whereas in this part, well, the maximum height is approximately 110 centimeters. What does this mean? It means that even if the level is sufficient to prevent in the design condition the overflow, of course just a small wave will create some overtopping. The cross-section of the keys is presented here. This is the cross-section of the keys in A and B. You can see it is a vertical wall basically, and then there is this pavement formed by Mazzegni stones, and the difference between A and B is basically the slope of this pavement, whereas this is the key in the area C with these descending steps. In order to study the overtopping, we need to know what is the water level in front of the keys and what are the waves. So for the water level, we have to understand what are the closing scenarios for the Mo.Se. They are based on predictions. If the water level, including the expected error, has the chance to achieve here in front of Venice the level of 110, then the gates will close in advance. Therefore, it is expected that here the water level is lower or equal to 110 centimeters of the chart datum. Well, this is only the extreme case. More frequently, it will be between 90 and 100. For the wind waves, we have to look at the wind, and in particular the wind blowing from direction 120 degrees north. The possible wave have been studied in a companion paper that is presented at ISOPE in a few days, and well, as an order of magnitude, if the wind blows with a speed larger than... These are two cases of flooding of the Piazza, one in 2013, one is in 2012. The first panel here shows the significant wave height. The dotted line is the daily trend, so that you can see that mainly the significant wave height is due to passing ships, but not always. The second panel delineates the water level. These two are measured in front of Piazza San Marco, that is here, and they are measured in Punta della Salute. And the third panel is the wind velocity measured at the Lido inlet. In this case, the wind velocity is approximately 15 meters per second, and the direction is approximately 120 degrees north, so that this wind actually contributes to generate large waves, and you can see that waves up to 30 centimeters were observed. In 2012, a similar case, but the wind was up to 25 meters per second, and in that case the waves, the measured waves, are of the order of 40 centimeters. This program is based on this information, so that 5 wave attacks were considered with a wave height ranging from 20 to 75 centimeters, 2 wave steepnesses, and 3 different water levels. 90 centimeters, 1 meter, and 1 meter 110 centimeters. And everything was scaled in 1 to 5, and the 3 cross sections were all tested. This is a longitudinal view of our wave flume with all the structure on the right. This is all described in the published paper. This is how the vertical wall looks like, and during the building and at the end. And this is section C with the descending steps. Section A and B are both characterized by a vertical quay, but you can see that the sloping wall is different. In one case, the top of the pavement is 110, because then the pavement slopes down, whereas for section B, the pavement continues to raise up to 117 centimeters, like for section C, where there are the descending steps. This is basically the investigated phenomenon. In the lower panel we have the flume, and in the upper panel we have this case with the tide basically, the tide level basically at the height of the quay. The results in terms of the expected overtopping along the quay have been recently published, and the most critical section is section A. It is vertical, with the crest height of the pavement approximately 110 centimeters. In this case, the overtopping is really excessive, and some mitigation measure is necessary, otherwise too much water floods from the lagoon. So let's give a look again at section A. The quay is water level 110, so and there is a slightly sloping pavement up to 110 centimeters. Clearly, when the water level is 110 centimeters, just the smallest wave will produce over. And the idea is to test two possible configurations. Configuration A, with this barrier placed just at the edge of the quay, so since the top of the quay is 110, then the crest freeboard is at level 140. And in configuration A2, then this vertical barrier is placed inward of the edge, just 2.5 meters inward, but of course 2.5 is in real dimension, and the top, since there is this small slope of the pavement, then the crest fiber will be 145 centimeters. These are some pictures for configuration A1. These are taken for water level 110 centimeters, a significant wave height of 50 centimeters, and one of the two steepnesses. And what you can see is that the wave is really reflected from the barrier. Of course, it overtops the barrier, this extreme wave height, but then it jumps down, creating really a big impact in the inner part. And this impact is a little dangerous, we believe, for the Mazzegni stone of the pavement of the piazza. So this is the first measure, mitigation measure, configuration A1. And the second mitigation measure was this case, where the barrier is placed a little bit inward, and you can see with the same wave height that the impact on the pavement pavement is much smaller, and basically also the overtopping is smaller. As we see from this graph, this is configuration 1, barrier placed at the edge, and you can see that the maximum discharge here is approximately double than the discharge that we find in configuration A2, which you should also benefits for the fact that it is 5 centimeters higher. We can also compare the wave overtopping achieved with the two configurations with presence of the barrier versus the case without any barrier, and you can see that there is a huge reduction, a factor going from 3 to 6, 3 for configuration A1 and 6 for configuration A2. Clearly, in this mitigated case, it will be possible to get rid of the overtopping through the new specifically designed drainage system. For configuration A2, we also consider that it was a little bit difficult to design what would be the load over this barrier. So we measured the load with the 3 load cells here, and this load is presented in this graph. This is scaled with a sort of hydrostatic, proportional to hydrostatic load. So rho g from d is the height of the wall, 40 centimeters multiplied by hs. This is a sort of hydrostatic reference, and proportional to hydrostatic load. And you can see that this total force is of that order of magnitude. Of course, a little larger due to the impact of the wall. So, in conclusion, physical model tests were carried out in the maritime laboratory of Padova University in order to measure the overtopping discharge expected to flood Piazza San Marco when the Mo.Se will be operational. First, recently published tests were presented, proving that the expected overtopping discharge is excessive in the absence of some mitigation measure. In fact, a temporary barrier to reduce overtopping is foreseen and will be built, very likely. Then, new tests were presented analyzing a 40 centimeters high barrier in 2 configurations, with the barrier placed at the edge of the quay in configuration A1 or 2.5 meter distance in configuration A2. For both cases, the discharge is reduced to acceptable level. However, we believe configuration A2 is to be preferred. First, because it is more effective. Second, because during the tests, large jets were observed that may have some consequences on the pavement stability in the absence of an additional extra protection. And finally, the measured load applied to the barrier in configuration A2 were presented, providing a useful recommendation for design. Thank you for your attention.